in this video, what we're going to do is look at the tipping problem physically. And then in the next video, we'll look at it on paper to see what the math of it looks like. So, a tipping problem. So let's say I have an object. Let's say I have a book, present book that I'm reading. There we go. And I want to talk about tipping it over. Now, there's a lot of different ways I could tip it over. I could exert a force on it forwards, right? That would cause it to tip, or backwards, right? I couldn't exert a force downwards like this, or I could exert a force like this. That would cause it to tip over, right? But the question is, when does something tip, all right? And so what we have to think about here is the concept of center of mass and the force of gravity, and specifically the torque due to gravity. So let me just turn my Harry Potter book around here. What I've done is I have attached a piece of tape to a quarter, and I've attached that piece of tape to where I would suspect the center of mass is. Now, it's not exactly a uniform object, but reasonably enough, we would say that this is the geographic center. Obviously, the geographic center would be halfway through the width, but there we go. And so what I've created is something that's called a plumb bob, which just hangs straight down. It's a fancy name for essentially a mass on the end of a string. It'll always hang straight down. But notice what happens here when I start tipping it. That plumb bob hangs straight down, but what you're noticing here is this is the pivot, right? So if that's the pivot and there's the plumb bob, so that string is hanging straight down. Yeah, there we go, right? And what you'll notice here is that if this point is the pivot point, that this gravity force does not act through the pivot, and therefore would create a torque in this direction. So from my perspective, that's clockwise, so I think that's counterclockwise from your perspective. I'm not exactly sure. I'm just going to speak in terms of my perspective so that I can be coherent in this video, right? So, boom. So if I let go of this, a torque will arise, which will bring it back to this position, right? Now, obviously, I'm exerting a torque here to hold this thing in static equilibrium, but what we're interested in tipping is, at what point will the object continue past and fall? So as long here as this force creates a clockwise torque, when I let go, it's going to go down to this situation. Now, what you'll also notice here is, look at the height of the center of mass. When I start tipping it, notice that the center of mass is actually moving upwards, right? So what's actually happening here is that the book has to be gaining potential energy when I'm tipping it, if the center of mass point is moving upwards, right? So at some point, though, when would that be that no longer the gravity force causes a clockwise torque in this direction? And that point would be exactly when that center of mass is over the pivot. Now, technically here, I should be able to balance the book on this point. And notice it's very finicky that it will go in one of the two directions, but there should be exactly one point in which that happens. And if you're thinking, oh, well, that's interesting, a torque arises to push the book away from that one point. If you're thinking unstable equilibrium, you're absolutely right. This is a point of unstable equilibrium. What's the definition of a point of unstable equilibrium? Hopefully you remember that an equilibrium is a point where the potential energy is maximized on that graph that we talked about, right? Where U was a maximum. Oh, notice here that the center of mass goes up, 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 up. Then when you get past that point, it goes down. Yeah, potential energy is maximized at that point, right? So here, the torque is trying to bring it to a stable equilibrium. Here, unstable equilibrium, the torque is trying to bring it away from the point of unstable equilibrium. So what is that unstable equilibrium? That unstable equilibrium is what we're going to call the tipping point. And that tipping point occurs when the center of mass is directly over the pivot, if that pivot is one point, right? Or if you want to think about a stable object in terms of will it tip over, I want you to think about this base here as what we'll call an area of stability. as long as the gravity force acts downwards through the area of stability, when you move it away from that stable equilibrium, a torque arises to bring it back to that stable equilibrium, right? So as long as the force of gravity has to support underneath it eventually, that object will be stable. So we're going to look at another system that uses that same idea, right? So here we go. And here I showed you this system in an earlier video, in fact, in the introduction video. So now what we want to do is look at how far can I, let me get my soup out of the way, how far can I get my book over the edge, and let me move it to landscape here. How far can I move it over the edge until the book tips? Now, theoretically, what that should be is, and you notice the piece of tape there, right there, boom, that piece of tape is now not over the edge of the table, and so the force of gravity creates a net torque that causes the thing to tip. So as long as the center of mass of that one book is, and I just knocked my brooms over here, okay, as long as that center of mass point is over the table, then the center of mass is over the area of stability and there's no net torque due to gravity. So how far can I go? Well, it should be, if you think about it, just half the distance, because that's where that center of mass theoretically should be if that book is uniform. So now if I had two books, well, what's the logic here? How far over the edge could I do? Well, at L/2, once again, that's where the center of mass is. But if I start displacing the books relative to each other, the center of mass of that system now just has to remain over the edge. So how far could I go? Well, I know that the top book, as long as it's L/2 is exactly at the edge here, the top book shouldn't tip relative to the bottom book, right? And I think I've got it just about that. Right, so now that's L/2 out. Notice that's how far I was able to get it when it was just the two books stacked directly on top of each other. But now I can actually start moving the whole system out, because this book is balanced over this book, but the center of mass of this system holistically is somewhere here. And as long as that center of mass point of the system is there, the books will remain in balance, right? And so now the system is more than L/2 in total out from the edge, and I could find that tipping point about where that is if I know where the center of mass of this system is, because that's going to be the idea, that if I continue to stack books, the top book is always going to be L/2 out from this book, and this book is going to be a certain amount over from the table. But then think about it each time, is that if I just put another book underneath and just keep moving it out until the center of mass of the system is over the edge of the table, that's going to be our tipping point. So that's going to be the logic of a problem that we're going to do together, problem 22.